Every story, there comes a moment of confusion, a point where direction fades and uncertainty takes over. This is one of those moments. Asan na kaya yun? Dumaan na ba ako dito? Teka, ba't ako nandito? Guys, sino kaya to? Grabe talaga, inasar pa talaga ako. O kaya mahanap yung building na yun? Oh, sino naman kaya to? I swear, pag ako talaga inaasar pa nila. Campus navigation app? Matry ko nga.
What's up everyone? If you're lost at the campus, watch this. I'm going to introduce you to a website that makes sure that you are never lost again. And it's called navi.cspc. It is a campus navigation app designed to help you students, teachers, and visitors navigate CSPC. So, in our canvas here represent a simple map of the campus of CSPC. The buildings are represented by these nodes, and the pathways that connects each buildings are these edges. So you want to navigate to your class from the entrance. Just click on the nodes you are in and click the shortest route button. Search for the building you seek, and now you are where you want to be. You can try this as many times as you want, as many times you are lost. Now, to encourage creativity of our students, I'm going to introduce a feature that lets you create your own campus. Now, let's explore these buttons. To add building, first, click on an empty space on the canvas, then click on the Add Building. Run your creativity wild. Add as many buildings as you want. To add pathways, select 2 buildings and click on Add Pathways. Next, if you want to check the reachability of your buildings, you can try the reachability button. If there are no pathways that connect those buildings, the program will tell you that it is unreachable. You can skip this next part. In this section, we are going to explore how this app works in codes. My friend here will discuss to you the foundations of this app.
So now we will delve into the Python implementation of our campus navigational system. So just a brief overview of the system. We decided to display the system visually as a web page, and then we used Django for the backend, and then for the front end we used Next.js. For this implementation or this video output, we will only be focusing on the graph operations, which will be found inside the backend and inside the campus app, and then here in services, and then graph.py. Let's just start first with our headers and then our imports. So at the very top, we imported annotations from the future random method. This just essentially helps in type hint referencing. And then the next is from the classes. We imported data class. This is a decorator, as you can see it is used here in line 10. This automates the boilerplate for constructing simple classes used to hold data like representation, and then etc. etc. And then the second import, we imported heap pop and then heap push from heap-queue. So heap-queue is it essentially provides a binary min heap implemented as a list, and then we imported its methods, heap push and heap pop. This adds or pushes an element, and then heap pop, this pops the smallest element. This will be useful for the Dijkstra's algorithm for the priority queue. And then below it is we imported type hints. This is just used for type hints and for readability and static checking, which is important for this project. And then the last import is this allows to utilize Django's ORM models that we have created. So we have created a model for a building and for a pathway. This is our graph nodes, and this is our edge models. So now we will head on to our class, this path result class. This is just essentially a small container object turned by the shortest path and the reconstruct path here, and then the reconstruct path. So we only use this to keep the return values tidy and somewhat descriptive. Now moving on to our first function, which is the build adjacency. This creates an adjacency list. So what it does is it takes an iterable of pathway objects and it builds an adjacency list, which here it directs it, pipes it into a dictionary, mapping the source ID to an integer, and then the list of target ID, and then distances. This This is used for representing a directed weighted graph. So edges from our source ID to our target ID is appended with weight distances. Our shortest path function, this is where we implemented a Dijkstra's algorithm. So so if start ID is equals to end ID, it tries finding if the buildings exist, otherwise it will return none, and if it found, it will return the path result and then the building and then its start ID. Below that we have an adjacency variable. This helps loads all the pathway objects from database into memory and then builds adjacency using our function above. Now here in distances, this essentially holds the best known distances from start to each node. So we initialize it start to 0. The previous one, this will be used to reconstruct the path of the previous node to its parent node, and then the visited will hold all the nodes whose final shortest distance is known, or if we pop that, then that means that we have already visited that node. And heap, this will store the priority queue of distance node, and then it is initialized with 0 as the position and then its start ID. Now here we have a while loop. So this says that while heap, we pop the node with the smallest tentative distance, and then we skip already visited nodes, and then if the node is not visited, it will be marked as visited, and then if we reach the end ID, we can reconstruct now the path immediately and then return it. Here inside the for loop, this is a sort of a relaxation step. It iterates through neighbors and then compute the tentative weights or distances, and then it updates the distances and previous when shorter path is found, and it will push the improved estimate onto the heap. Here it will return the distances, it will return as infinity if there is no neighbor discovered. Construct path function, this just build the ordered building objects. So this reconstructs the path of node IDs by walking previous pointers backwards from end ID to start ID. So the chain becomes an ordered list of node IDs from start to end after the reverse. Here in buildings variable, we query the database for building objects, and then with its matching IDs in chain, builds a mapping ID to the building, so we can reorder them back into a chain order. Here for our is reachable function, so this just checks if one node is connected or can be reached from another node. So this uses depth first search. Since we are using weighted nodes, we utilize the depth first search instead of breadth first search. So essentially, if start ID is the same ID, it will if the ID is same, it will just check the existence in the database and then return a boolean if it exists. Here in adjacency, it builds the adjacency and prepare the depth first search stack. So we have a while loop. This is just a classic the first search. We pop the node that is and then mark it visited. Then for each neighbor, if the neighbor is the end ID, it will return true. So it is meaning that it is reachable, and otherwise it will just push a neighbor to a stack to further explore. So for our final function, the get full map, this just exports all nodes and then edges to the front end. So we query the database for all the building objects and all pathway objects, and then it will get the related building objects in the same query. It will now then return a JSON serializable dictionary with buildings and then pathways and its respective model attributes.
That's it. In data structure, there is something called traversal. Traversal is a process that visits all of the nodes connected via edges. This is done so whether for searching or printing all of the data in the tree. In real life, however, that's just called being lost.
Ayos, alam ko na kung saan. Uy, hinintay mo pala ako. Uy, andyan na ka pala. Oo, maraming salamat sa'yo. Walang problema. O ito, handshake tayo para bros tayo. Liga na. Salamat, Navia.